All right, so let's go ahead and look at 7.2. In 7.2, we're going to be talking about the direction of reversible reactions. So in the previous video, we had looked at some information. So let me go ahead and put that information here on the screen, and then we can continue forward from here. So in the previous video, what we had looked at was equilibrium curves here. So we saw that the reactants here in red and in blue decreased over time, and the products increased over time, and these should be a little bit lower. So let me just go ahead and adjust that just a bit. I don't know if I can, but let me try. There we go. And so the main idea here was that as time increased, we were able to see a point where the atom or the concentrations kind of flatlined, and all I did was move this down. But the main idea here is when you get to this point in time where the concentration flatlines, and my drawing's not drawn the scale here, this point in time is known as K, or equilibrium. Now the question is, how do we tell which direction the reaction is going to go? Well, it all depends on the value of K. So one of the things that you'll need to be able to do for this section, or the skill that's really required of you, is to know how to identify the expression that is used for K, and then also to be able to interpret the value of K. So let's begin with the general expression. So what does that expression look like? So let's move this over to the side. So if we're talking about K, K can be a couple of items. And so if we're using this generic equation, let me put that generic equation back up. So here we have the generic equation, compound AB reacting with compound CD, and it will form the two products here at the very end. What is not written here, which I will add now, are the coefficients A, B, C, and D. So the reason that these are important is that we need to make sure that we represent these coefficients inside the expression for the equilibrium value. And K is represented in the following way. First off, we know that these items over here are the products, and we know that these values over here on the left-hand side, these are the reactants. And so from a very generic point of view, K is going to wind up being the concentration of those products divided by the concentration of the reactants. And from a generic point of view, this kind of is an easy thing to do, because K then gives us a couple of outcomes that we can look at. So let me readjust this a little bit. So K can actually be a couple of numbers. At equilibrium, if the concentration of the products is the same as the concentration of the reactants, for example, if we do the multiplication of both of the products and we multiply, and just generically, let's say that the concentration is 2 molar, and we do the same thing for the reactants and find out that the total concentration here is 2 molar for the reactants as well, well, 2 divided by 2 is ultimately going to give us 1. So that kind of gives us one of the outcomes for K. And so K then can actually be the following. K can have a couple of outcomes here. K can be equal to 1, and this is going to be at equilibrium. And I'll just say at equilibrium here. But also K can be greater than 1, or K is less than 1. And it's with regards to the other two that we need to pay attention, because what we're saying here is when K is greater than 1, what we're saying is that the concentration of the products is going to be greater than the concentration of the reactants, and that's what's going to give us a value greater than 1. So for example here, just to illustrate this point, and let me zoom in on the values of K, or zoom out a little bit here. When K is greater than 1, and so that would be K greater than 1. This is kind of saying something like, just to accentuate the point here, let's say a concentration of 3 molar for the products. And we're going to divide that by a concentration of 1 molar for the reactants. In this case here, if we do the math, the concentration or the value of K is going to be 3. So this value here is definitely consistent with K greater than 1. But what about K less than 1? Well, what this is indicating is that the reactants then are going to be greater than the amount of the products. And so if we do that example, use a slightly different color here, when K is less than 1, this is about the same thing if we were to invert the numbers. Instead of putting 1 molar in the bottom, Let's put the 1 molar up top. So conceptually here, what we're going to get is the following. 1 divided by 3 molar. And so the number here is approximately 0.33. And you can definitely see here that this number is significantly lower than 1. But that just goes to show the point here that we're looking at the concentration of the reactants versus the products. So in this case, the reactants are far greater than the concentration of products. And so the reason that this is important for us is because when we talk about K greater than 1 and less than 1, what we're really saying here is the following. We're saying here that in K greater than 1, what we're saying here is that the products are favored. And in the other side here with K less than 1, what we're saying here is that the reactants are favored. And so this is going to give us a little bit of an indication as to which way the reaction is going to go. Now to tie this all together down in one nice little package, let's move this over a little bit and focus on these values for K. So when you have K values, the most common thing that you're going to be given is maybe they give you a reaction, but then they give you a value. Let's say here that a K1 is going to be 2.1 times 10 to the negative 4. And let's say they give you another one for a different compound. Let's say a K2 is going to be 2.1 times 10 to the negative 11. Now, if you refer to these numbers here, the one number that is closest to 1 is the one that is going to be preferred. So in this particular case, 2 times 1, the coefficients are the same for both of these, and all we have to look at is the coefficients, or the exponents. An exponent of negative 4 and an exponent of negative 11 should tell you that the bottom number here, this one here that I'm going to underline in yellow, this number here is smaller than the number above. So that means of these two reactions, separate reactions here, the one with the K value 2.1 to the negative 4 indicates that this reaction is actually going to be a little bit closer favoring product formation for the reaction that it represents as opposed to the one on the bottom. Since the value is a negative 11, it's a small K value, so there is a little bit of product being formed, but a lot of it is going to be favoring the reactant. So a lot of the concentration that is going to be present here is going to be more on the reactant side. So based on these values here, what we tend to see here for this one here, because of the value of 10 to the negative 4, the reactants are still favored on both of these, but the one that's going to give us a little bit more product generation is the one at the top here that I'm going to underline in blue. Now, the one thing that I need to make sure that I do is let's go back to that original equation that we had, and it's right here. So what I want to do is kind of zoom in on this. And what I did not share was how do you get the expression K for this reaction, whatever reaction it may be. So let's go to share this at the very top. So for this reaction that I'm going to go ahead and box in yellow, the K expression is going to be written as follows. It's going to be equal to the product concentration. But notice here we've got two separate compounds. So it will be the concentration of the first product, AD, and we're going to raise it to the power identified as the coefficient for AD, which in this case is going to be C. And then we're going to multiply that times the concentration of CB raised to the concentration power of D. And then we're going to take all of that and divide it by the concentration of compound AB raised to the power of A. And then we're going to multiply that times the concentration of CD raised to the power of B. So this equation here at the very top is the reaction or the expression for that equilibrium, which is known as the K expression. If you know the values of any of these products or reactants, simply plug the information in, assuming they're giving you a K value, and you can determine the concentration of those when provided. Now, there's going to be a situation a little bit later here where we're going to have to figure out concentrations at equilibrium, but we'll address those then. For right now, these are the concepts for 7.2.